To show that x over 1 plus nx squared converges to 0 uniformly on the real numbers, we might first try the estimate where I bound the absolute value of this function, which I'm trying to show that this quantity goes to 0 uniformly. I bound this above by simply removing the 1 in the denominator, which makes the denominator smaller and thus makes the fraction bigger. In doing this, I get the following expression, 1 over nx. Okay? So for x not equal to 0, this expression converges to 0 pointwise. Okay? So this converges to 0 pointwise when x is not equal to 0. And so we might just think, well, at x equals 0, this expression is clearly 0. And then when x is not equal to 0, we can just use this estimate. However, this is a pointwise estimate, and it's actually not uniform. Notice that if you take the limit as x goes to 0 for any fixed value of n, if you take the limit as x goes to 0 of this quantity, it's going to blow up to infinity, which means that your choice of n must depend on your x location. You cannot have a uniform choice of n, which makes this quantity less than epsilon. Okay? However, it does converge uniformly on x not in an interval minus epsilon epsilon. So if I cut out a small neighborhood of 0, then in fact this does converge to 0 uniformly, as we'll see. The next estimate that I need is a somewhat less obvious estimate. It's easier to see algebraically, but more difficult to come up with in practice, which is that this denominator is just positive, so we can just throw it away and bound this above by x. The reason why this is hard to come up with is because that's probably in many cases going to be way too much to throw away. However, notice that this quantity is independent of n. First of all, it's independent of n, and in a neighborhood of the origin, this is going to be less than epsilon. So I can use this bound to cut out a neighborhood of the origin, and then outside of that neighborhood of the origin, I can use this bound to show uniform convergence. So let's write the proof. So I fix my epsilon, and then I choose capital N such that x over 1 plus nx squared, which is less than or equal to 1 over nx, which is less than or equal to 1 over n epsilon, and I want this to be less than epsilon, for all n greater than or equal to n, and x in the set negative infinity to negative epsilon union with the set epsilon to infinity. So essentially all real numbers with an epsilon neighborhood of the origin cut out. And in doing this, we see what our choice of n should be. Our choice of n looks like is going to be 1 over epsilon squared. And maybe take the ceiling if you are required to work in the natural numbers. So clearly, if for this choice of capital N, this inequality will hold. And you can do the algebra and try to show that on your own. But notice that also x over 1 plus nx squared is less than or equal to x, which is less than epsilon, less than or equal to epsilon, I should say. For all n, independent of my choice, this expression doesn't depend on n. x in interval negative epsilon, closed interval negative epsilon to epsilon. So this tells us that for all n greater than or equal to capital N, we have that x over 1 plus n x squared is less than or equal to epsilon for all x in either of these two regions. However, the union of these two regions is just the real numbers. So this actually is all of the reals. And this is by definition uniform convergence to 0. You can see that my choice of capital N only depends on epsilon and not on x. All right.